Writer, and this is our project on optimizing compression neural networks for weather and climate data, and the repo will be there at the bottom. So our work is based on an existing paper called Compressing Multidimensional Weather and Climate Data into Neural Networks. It's a 2023 paper out of Zurich, and they essentially overfit a deep neural network and save the weights as a lossy compressed version of their climate data. Essentially, this means that they learn a continuous function that maps the coordinates as the input to the atmospheric data, pressure, temperature, etc., to the output. This ends up achieving anywhere in the range of 300 to 3000 compression ratio, and this is not bounded. They test in smaller networks, and this can increase almost unbounded as long as the networks are smaller. And it often, as they show in their paper, outperforms state-of-the-art lossy compressors on MA and RMSE, which are quality metrics. And this also tends to give what they consider free interpolation, because you can provide an arbitrary data point that may or may not have existed in the original data set, and then get an output from the model without having to run an interpolation on your discrete data points in the original data. So this is their model architecture. As you can see, they have their discrete grid points and they have their interpolation. They do a random sampling, transform their data into from longitude latitude to Cartesian coordinates, put it into the Fourier features and transform them so that they preserve the spectral bias. They learn the high frequency features and low frequency features. And then they do a series, they do 12 in the paper and we use 12 in ours, fully connected layers with feed forward and batch norm and some skip connects to keep the gradients flowing smoothly. And then they compare this with an MSE loss and quantize to floating point 16 and save the model to disk. And that's their compression pipeline. So the problems that we identify with the original paper. The original paper obviously identifies that climate change is significantly increasing in size and that compression is very important. And then they give a very fast random access speed and decompression speed with their method at the cost of incredibly slow compression speed. They specify that they use 2 days in compression in training time to compress the model. So it's very slow, even in comparison to CPU-based state-of-the-art lossy compressors like SC3. And the original paper doesn't look at further sparsification or quantization techniques, even though they do say that would be an interesting next step. And the experiments against other compressors, in my experience, are limited at best. So our contributions, we do a 100x speedup on the training on a single Ampere GPU, my local one, and it replicates the experiment with this accelerated training, giving even slightly better metrics than the original paper. We tested our accelerated neural network compressed data against SC3 with some more unique characteristics, such as optimized dimensionality ordering for better compression with the Lorenzo predictor. It identifies some reproducibility questions, considering we weren't able to get SC3 to compress the same as theirs. And it compares against tighter error bounds for compression, as well as other error types given to SC3. And then finally, we did a small amount of testing of the compression of the model itself, but due to time, we didn't get too far into this, but it was kind of an interesting next step. You can get about 10% extra compression if you just zip the model weights. And then aggressive pruning and sparsification techniques either generally didn't push enough compression for the cost, or they lost too much when they compressed enough. So the first one is the accelerated training. They take 2 days to train on 3 3080s, about 0.07 iterations per second on my personal testing. And then to accelerate this, we use mixed precision matrix multiplication in the training process. And then this allows it to use the accelerated tensor cores. And then we used an improved data loading strategy with explicit CPU data interpolation and enforcement of contiguous tensors and data types. And then optimize the data load configuration to better utilize the GPU. This resulted in a 100x speed up in training, going down to 7 hours on a single 3080 Ti. And here we can see the data set for dataset 2, the geopotential at 0.25 resolution, 2016. Specifically, this is going to be around the time when Hurricane Matthew was forming. So there's 11 pressure levels, and the most important one to pay attention to is the 500. So that's the one we've pulled out to view. You can see the top 3 images are the original geopotential, the reconstructed, and then the difference, so the error. And you can see that we do a very good job of reconstructing the geopotential generally across the globe at this pressure level, given the accelerated training framework. In the paper that they point out, their main issue is that they aren't able to capture the sharp changes very well. So here you can see Hurricane Matthew forming very, very strongly on the left-hand side, and then the center, you lose a lot of that strength, and then the error, you can very much point out the fact that Hurricane Matthew isn't being fully represented the way we want it to be. And this is just a weakness of using a neural net to do this type of training, to do the compression. It's just difficult to learn those features. So SC3 is a error-bounded lossy compression framework from the FC framework. And we test against that to see what the relationship is between a more standard lossy compression pipeline and this very strange neural network-based approach. So the original data is around 17 gigabytes. And then if you use a climate data specific format that you download the data in, that's NetCDF based, it's about 5 gigabytes. The model in floating point 16 is only 14 megabytes, about 1200x compression, and then about almost 400x over the compressed data file that you download, which is significant compression for this type of data. SC3, they use an ABS, or an absolute error bound, of 1,000. It's about 6.4% error allowance. They report a CR of 358, and we report an error of 735 for the 500 pressure level. And then for an optimized reordering of the entire data set, we see around 153. So somewhere in that middle range they're reporting, but I'm not entirely sure how they're achieving it with the settings that they've provided in the paper, just because we see either much lower on the entire data set or much higher on a single pressure level. And then we also test with a relative error bound of 1e⁻², and we see that that results in a CR of 115 with around a 1% error bound. So you can see it does drop quite significantly, but you do retain significantly more information. So here we can see the top is the SC reconstructed from the absolute error bound of 1,000, and then the bottom is the relative error bound of 1e⁻². You'll also notice the far right graph, the bottom right looks far worse, but that's only because the scales are much smaller. It's much better overall. And then the two pictures to the left of those can demonstrate that a little bit better. You can see that the features are much more smooth and flow nicely in the relative error bound case. So you do get a lot of trade-off for that error bound and for the compression ratio. And then finally, model compression. We attempted to try and prune the model. We tried a few pruning methods, but didn't find any that really ended up, producing interesting enough results to report, either resulting in very minimal compression or resulting in just absolute nonsense on the output side. And we didn't have enough. We ran out of time to do further testing, but it seems that basic strategies or very preliminary results don't show a lot of initial success, or a lot of success in achieving past what these already great compression ratios are able to get. So in conclusion, neural nets are still poor at these high fidelity information capture, such as when you're dealing with hurricanes. Even using a Fourier transform to combat the spectral bias, the compression ratios and general error metrics of the neural networks are very impressive, And the learning of continuous function has interesting benefits, such as in the original paper, they use this kind of free interpolation to have a fast data generation method for a CNN-based architecture for training data. And then finally, state-of-the-art lossy compression techniques can still be better at capturing the important relevant events, but obviously at the cost of a significantly lower error bound. So there might be a mixed solution approach that achieves the best of both worlds. And thank you very much.